Right, I think it's time now we can start. So welcome everyone to this webinar. So it will be monthly. So if I mute, so everyone can mute, please. So I'll try to mute everyone from here. Okay, so again, welcome everyone for this webinar. It will be a monthly webinar for the MODENERLANDS cost action. So we'll start first with working group 1, and starting from today, and then next month will be working group 2, and I can see that Enzo is here. So Enzo will, are you here, Enzo?
Yes, I'm here.
Excellent.
Hello, Hassan. Hello, everyone.
Hello, Enzo. So Enzo is the chair of working group 2, and he will send some information about the next webinar about working group 2. And then the third webinar will be about working group 2, and I don't know if Robin is in here. So Robin will send some information about the webinar for working group 3 on time. So this will be in April. And then we'll repeat everything again, working group 1, then 2, then 3. And I will take this opportunity to thank you all for joining this webinar today and showing interest in this cost action. And also to ask if any one of you is interested to present your work in the webinar, to contact the chair of the working group or the working group leader or co-leader. So for example, if anyone from working group 1 is interested to share his research, then please contact me or Anina. And then we'll put you actually in the time for this webinar, and the same for working group 2 and working group 3. Just contact Enzo or Robin. Right. So we have our first presenter today is Teresa from Portugal. She will talk about the energy resource offshore wind energy resources. And thank you very much, Teresa. And I will give you the mic now to start the webinar. And also, I will give you the right to share your screen if you would like to.
Okay. So I'm going to share my screen now. I think it's this one. Yes. Okay, so thank you very much for organizing the webinar. The topic that I'm going to talk today is was somehow already approached in our first meeting, but nevertheless, I think that this is a very interesting topic to deal with and to go ahead with marine renewables development. So today I'm going to dedicate this talk mainly to the wind resource assessment for planning specifically, and then I will also go a little bit through some planning methodologies for this purpose. So I will give a very, very short introduction on this. And then we will follow these steps that are here on my slide, and I will end up with some final remarks and some research topics on the floating offshore sector. So I think that all of us are a little bit involved or very involved in the offshore wind energy sector at this time, and especially because we are now living an energy crisis. So I think that offshore it is an area that will have a very strong contribution for this. So nevertheless, in order to maximize all this contribution that we can have in this topic, we really need to have an effective strategic development plan. And this will include several steps where we have one of the most relevant, which is the offshore wind resource assessment. And then in order to identify and select suitable sites for the development of the projects, whether they are wind or waves or other type of systems development, we need to identify all the existing restrictions that will prevent you from installing your systems. And then a third step that I'm not going to talk today, but it can be developed in another session, is the component related with the socioeconomic and economic feasibility analysis of the projects. So all this work that I'm going to present is the result of a national project that we had in Portugal some years ago, which was called Offshore Plan. And although the project has ended officially in 2020, there is the need to update all the information and to continue developing the work in order to be able to develop the sector nationally. So a special planning methodology for offshore projects can be defined, as I stated here. This is only one of the definitions that we can give it, which is information and georeferenced information that defines the set of operating restrictions managed by a geographic information platform capable of connecting and relating the spatial information normally designated as layers. So we need all this. We need to have the wind resource assessment mapped and georeferenced. We need to have all our restrictions, and we need to have a lot of information that is very heavy. So in order to do this, we will use for wind resource assessment a specific methodology, and for the planning, the geographical information systems and all the techniques that are associated to it. So the results that we are going to achieve can be many results. And in this case, we are going to find suitable areas for the development of these renewable energy. So we have a lot of information that is available. We have existing databases with information about the restrictions. We also need to work on the free areas, those ones that we identified in the first approach that are suitable, and the results will be inputs for further development studies. And this is on the side of the wind resource, because what you will have is a large map of your resource parameters that you then will need to develop a little bit further locally. And of course, you need periodic updates of the database, which are of utmost importance for this type of studies. So in terms of wind resource assessment, this is in fact a very important step for a plan for the exploitation of this type of renewable energies. However, and comparing, for example, with the onshore case, you don't have that many experimental campaigns going on. They are very expensive, especially for deep offshore regions. And when you have them, these experimental campaigns are usually located in very small areas, so that their area of intervention is not that large. And you also have some temporal resolution that may not be suitable. For example, you may not be able to collect your data for a large period, due specifically to the costs that it takes. So to achieve this goal, one of the solutions that can be used for larger areas is the use of mesoscale numerical models and their work. So these models have the ability to describe very important atmospheric phenomena for this type of renewable energy, such as atmospheric turbulence, stratification, sea land breeze processes, and so on. So here we are going to a little bit into the modeling. So let me just close this. Okay, so in the first place, you will need to establish your meteorological boundary and initial conditions. And what we know is that data from global model don't present the spatial and temporal resolutions that we are used to for onshore, for example. So they have very large spatial resolutions, higher than 25 kilometers. And also the time scale that you have is larger than 1 hour. So it's not sometimes very suitable for what we need. So we will need other data to feed our mesoscale models. And here in this table, I show you some of the data sets coming from reanalysis products that can be used for this purpose. But you will need to test them. You will need to see which one is the most suitable for your case. So, oh my God. Okay. So about atmospheric parameterizations, you will also need them to close the equations and use approximations to describe the physical process. And here are some of the examples of what we need: planetary boundary layer, cloud microphysics, and so on and so on. And here on this slide, I present, for example, one of the techniques that we have tried into the mesoscale modeling, which is a simulation. And this is a numerical technique that will combine several data sources. So you can have, for example, observed data with the first guess product from numerical prediction model. So this is not very usual in the numerical modeling. It's something that you don't see much in the literature, although it works really good in this type of with the objective that we have. So the most relevant parameters that we need in the simulation schemes will be, for example, the radius of influence, the time window, and the nudging coefficient. And here we can see, for example, the process represented in this graph. So now I'm going to show you the application of this type of technique. And this was work developed with the team of the project. Here I have all the authors and the involved people in this work. And also, just to add some information, it is related with activities 2 and 3 of this project, which was coordinated by my colleague, Anna Stanqueiro. So let's start with the steps that we need. So here on this slide, we can see the overall methodology that was used. So we have 2 initial steps where you need to define and to collect the observed data set, data series representing wind speed and direction, and also which were most of them obtained in buoys. We also use the floating LiDAR, a coastal LiDAR, and some coastal anemometric stations also for this purpose. And then an evaluation toolbox was developed, and this toolbox was used to compute some common statistics. For example, RMSE, bias, Pearson correlation, variable distribution parameters, and so on and so on. And it's mainly used to calibrate your model. And how is this calibration performed? This is paid by running several sensitivity tests with your mesoscale model, testing the different parameterizations in order to select the one that is most suitable for the region where you are working. And here on this big box, you have the 3 main steps that were computed. And what you are going to obtain in the end is a high resolution offshore wind potential atlas. Okay, so After that, we also go through a validation procedure using experimental data. So for the calibration step, the data that was used were some data obtained from different projects that were already where NEG was participating some years ago. And in this case, for example, for data from FP7 North Wind project, we used some data from oil platforms. And in demo flow project, we used data from buoys and LiDAR equipment. Also, in our hydrographic institute, we have some buoys that are some data from buoys that are publicly available. Some of them are commercial, so we can also acquire them. And we processed all this data for the calibration step. In terms of simulation data, we used satellite data in this case. And we have considered two typical periods for summer and winter for this process. So we have run the model in 3 different domains using a one-way nesting technique. So the special resolution for the domains is here represented. In the first place, the domain was 25.25 kilometers. Then it was narrowed down to 5 per 5, and then finally for 1 per 1 kilometer. Computing where the data that we used was mainly until the 300 meters bathymetric. And why did we select this depth? Because it is the depth where we consider that the available equipment and projected floating wind turbines are available to operate. So we didn't go much further than this. So here are the steps for the big box that I showed you. In phase 1, we have identified the most adequate meteorological and initial and boundary conditions for the modeling. For B, the identification of the most adequate physical parameters using some of these products. And we understood from this phase that there were very, very small differences among the different options that were tested in this case. And also the identification of the most adequate simulation scheme and data were also processed. So what we saw from this is that the best performance was achieved with the data simulation based on the information that came from satellite in the ocean, and also coupled with the reanalysis from the Era 5 project. So these were the best solutions that we found. For the sensitivity tests, we have run more than 100 sensitivity tests in this project. And what we found is that the highest improvements in the phase of calibration were associated with the daily restart of the model, because every time we run a mesoscale model, if you start having some small errors, they will propagate during this. Restart the model daily, and of course recording all the results. This will have a very, very good performance at the end with smaller errors. And also the data assimilation. We have then just go through the remaining methodology in order to achieve your goal, which is the mapping of the wind resource on offshore. So validation. So for the validation step, we have used some data series that we had available. We have installed an horizontal LiDAR system in lighthouses on the coast of Portugal, and we have they stood there for periods of 3 to 4 months, and then the data were correlated with coastal anemometric stations. And we also had a vertical LiDAR system that was also located in 2 different sites on the coast. So first for 4 or 5 months in one location, and then 4 or 5 months on other location, and the procedure was very similar to the horizontal LiDAR. So in terms of results, comparing the simulations with your experimental data, we found that the statistical comparison was quite good. So the average bias error was only around 0.4 meters per second. And in terms of direction, the error was a little bit higher, but it didn't go higher than 15 degrees in all the locations. The thing is that for some stations, the correlation was not very good. But direction, we know that it's always an issue in this type of work. So here we have the main results. We have here the wind speed map until the 300 meters bathymetric, the wind direction map, and also the power density map. So these are the results obtained for wind resource assessment following the method that I have explained before. So about wave energy, this is not the topic for today, but I have changed some words with us about this. So I'm just going to put here 2 slides on this, in just some highlights for a future session on this topic. So this is quite different from wind resource assessment. So we can use, for example, numerical models to compute the wave energy potential, wave buoys, pressure transducers, satellites, and all of that. And you can compute your wave energy assessment using this type of products. So, and this is essential for all these top points that I have located here. So the agitation data may correspond to several parameters for significant height, peak periods, average zero and or energy, and all of these that are here. So based on these parameters, if we obtain them for several time intervals, which can be in a long period, we can make we can have several years of data, and this is possible to determine long-term maritime agitation statistics, significant height, peak period, and all of that. And with all this information, you can define the climate and wave energy resource for a given location. So this is something that we will probably dedicate some time in the next little bit about this in a different session. So these here are only some of the results, some of the statistical scatter diagrams for obtained in this project. So now some words about the identification of suitable sites for offshore wind installation. So we'll go through the planning methodology. What you need for this is, as I said at the beginning of this talk, is to use a platform that will enable you to manage heavy information and georeferenced information, which is usually very difficult to deal with if you are not using, for example, a GIS. You also need to collect and process all the restrictions and conditions that you can find and that you think that are needed for this type of work. And then define the regions according to the technology and correspondent characteristics. Once you have all this, you are able to identify all the suitable areas, and you can then do other procedures inside your areas. You can, for example, I wrote this in gray because this is not going to be presented, but it was also performed to identify the sustainable wind potential inside your areas, how much wind turbines you can install. You can do that, for example, according to the grid capacity that you have, and you can define the capacity to install in your areas according to what you are able to connect to the grid in that region. So this involves several aspects of the planning. So this is the overall planning methodologies. You will, of course, need to represent your wind resource in the platform in your GIS model, and you also need to calculate the energy production according to the technology you want to install. So if you want to test several types of wind turbines, for example, fixed wind turbines or floating wind turbines or different types of floating wind turbines, you need to compute the power production in a map. And then in what concerns the physical restrictions, I've just represented here some of them, but we may have much more. For example, one of the things that was not used here was the fishery areas, for example. And here in Portugal, we have several problems with that because we have handcraft fishery and the areas where they occur are not public. So sometimes you may have some problems in collecting your restrictions. So here you have the map with all the restrictions that were collected for this purpose, and they were divided by bottom fixed technologies, and is what you see here in this map, which is the rocky seabed. Okay, so for floating, you don't have much concern with that, but with bottom fixed technologies, you will need to take a look at this. So this is our economic and territorial sea, and of course the bathymetry is of utmost importance. Okay, so you need that will define the technology that you want to use. Then we selected 3 different wind turbine models for floating and fixed foundations. We have also considered some other parameters, some conditions, for example, electrical losses, wake effects, and also energy losses due to operational unavailability and curtailment if it occurs. Also, and this map presents all of that, you can also consider the available capacity per electric grid reception zone. Here we have, for example, the interconnection points inland, close to the coast, and also the consumption areas that are represented here, also very close to the coast. Conditions for the definition of possible configurations. So we have considered energy resource available. We have considered proximity to the electric grid substations 25 kilometers to the coast, and also proximity to consumption areas. also had to consider something related with the submarine cables, because it makes your project much costly. If you, as much farther as you go, it will be more expensive. So we have considered that the submarine cables along the coast must be submerged to a depth of 50 meters, and we avoided environmental protected areas and seabed with rocks. The GIS tool, and here I represent both scenarios, one for wind and another for waves, that was also computed, and some results. So what we have done was to build an interactive tool inside the GIS so that you could change your input parameters. So you can consider all sorts of restrictions, but for a certain project, in order not to make your model too heavy, if you don't have certain restrictions, you don't need to put them here. So you can establish the values for the bathymetry according to the technology you are considering. And you can also consider the value for threshold values for a number of hours of production at full capacity. And these are the results. So all the simulations that were performed here in this project were for several types of technologies. And here you have an example, for example, for the wind flow technology, for the high wind, and then for the fixed bottom jacket and monopile technologies. And what you see here in white over the resource is the areas where you cannot install. So we have considered distance to coast. We have considered all the restrictions that I have represented in my previous slide. And you know that all these areas are good to go. Okay. So some final remarks about the resource assessment. We found that the methodology with the improvements that it had worked really good. So we were able to produce a wind potential offshore atlas and validate it with good results. And we also found that although we still need some further research in terms of simulation procedure, it is a very good promise for the future to use this type of technique. So from our findings and from our results, it worked also very well. But in this area, there are still some things to do. We still need, for example, to research a little bit on land sea conditions for offshore modeling, uncertainties and estimation of the wind.
Teresa, I think you are frozen.
Source. There are this type of procedure that can still need to learn sometimes how to work. LiDAR information derived from satellite, a really good solution for the offshore sector. And also some research on improving forecast of wind power production, fast window ramps, and occurrence of extreme winds is still something that is on the researchers' table. Another thing is the end of life evaluation of the wind turbines, which is a concern that it's most applied to onshore. But if we look at the north of Europe, where offshore wind farms exist for many years, sometimes I think that it's probably something that we need to think also. And then all things related with O&M processes. You need, for example, to start or follow the trend in the introduction of robotization, which has proven in the projects that have been developed in this area to be very efficient. So this is something that is really going on in the offshore sector. And that's all from my side. I just placed here 2 papers that can related with planning and with resource assessment that you can consult, and where you have more explanations on this type of work. So thank you.
Thank you very much, Teresa. That's really, really good. We have some times for glitching on the voice, but I'm sure that everything will be all right on the recording. So I see that some people are clapping or making some applause for you. Thank you very much. Well, I think we have sometimes about 10 minutes, 15 minutes for questions, and I've recorded many questions for you, Teresa, here, but
oh God.
Yes. So if you have any question, you can write in the chat, or you can actually say it loudly. And if I can ask you, if possible, to open your camera, because I need to take some photos for the website. And I see we have Carlos here as well. So if possible, we'll start with taking the photo first with a big smile. Nice. So if you please can open your camera, if it's possible, for a minute or so, just take a photo and then you can close it later if you want. So anyone else like to open the camera? Yeah, thank you. Oh, that's great. So we still have Marian, Daraki, Roman, John, then Paul. Right, so I'll take a screenshot. Thank you very much. So now if you would like to keep the camera, this would be nice. If you would like to close it, that's up to you. So I have some questions for you, Teresa, and then if anyone else would like to ask a question, that would be great. So we have in Europe, we have the new European Atlas for wind. Can we use it directly without going for high resolution modeling? So what do you expect the error if we use the new European Atlas for wind resources? And I know that considerable resources has been done for creating this new European Atlas for wind, and has been done over 5-6 years.
Yeah, I think that for planning purposes, the new European Wind Atlas is good. I didn't, I might confess, I didn't use it because in this case, we started, although we started this project while the NEOA project was going, we had a very short time to finish it. And on the other hand, I know that the new European Wind Atlas has a resolution that is a little bit shorter than the one that we have. So we wanted to have a product that could be used with a little bit more with a higher resolution, so that you could, for example, test smaller regions in the coast of Portugal. Also, we had available data, so our validation could probably go well in the coast of Portugal. So we thought that this would be a product that could be a little bit more improved. you wouldn't be able to, for example, to build an offshore wind potential atlas for the whole Europe with a small resolution, or I mean a higher resolution, if I say that, a higher resolution. So if you are considering a very small region, you can do that without many effort. So I think that it was a very important project. We have participated in that project also. But this is all in terms of resolution of the grid. So
excellent. Thank you, Teresa.
That's but it's suitable. Yeah.
Yes, we have a question from Paul here saying that we are interested in the engineering use for wind. So we need wind direction and wave direction at the same time. Do we have any data available for these, for wind and wave direction at the same time? And I will actually combine this question with the question about the meteorological model. So can we use non-meteorological model to get the wind direction and wind speed without using meteorological model? Is that important to include it in any simulation as well?
I think it is. I think it is. The wind direction is really, really relevant. So it is the most suitable way to do it like this. The problem is, in fact, what is asking is the availability of the data. That is a major issue. Anyway, today you have several data sources that are publicly available. You can use, for example, in a very suitable way, satellite data for this purpose. So, and there you can retrieve with not much effort the wind direction, and also for waves. So it is possible to have that data coming from, for example, the Copernicus services. So yeah, and buoys all over Europe. So I think that today we have many options for this.
So we have some data available for the wind direction and wave direction at the same time.
Yeah, I think we do. I can for if you contact me in a later stage, I can also put you in contact with our with the colleague on this team that worked with waves, and we can give you some more information on this and some links to find the data.
Okay, Paul, if you don't know the email address for Teresa, just contact me and I will send the email address for Teresa, please.
Yeah, do that.
Okay, any more questions from the audience? Well, if you apologize me, I have some other questions if you don't have. Well, Teresa, you use some experimental data to calibrate the model. And if I understand correctly, you use the same experimental data to validate the model. Is that correct?
Yeah.
But if you use the experimental data to calibrate, it's definitely the simulation will give good results compared to the experimental data because you use it for calibration. So how can you use the calibrated data to validate the model?
No, the thing is that the data series were different. So we used some experimental data for the calibration and satellite data. And then, because these data were available before the project start. And when we started the project, we have installed several LiDARs, not several, two. Not many, 2 LiDARs, and we have left also some of our meteorological masts that are operating on the coast to correlate them, because we have some met masts that are operating for many years. So we were able to correlate the LiDAR data with the met masts.
So they are not the same set of data.
They are not the same.
Okay.
They are not the same. So the calibration was made with a set of data series and the validation with other data.
Thank you for the clarification. And also, you showed the results for the area that is potentially good for installing the energy, wind energy farms. Are these optimized? What I mean by optimized, have you take into account sustainability there about the life cycle assessment for the wind turbines? And also, have you considered taking this out far away from the offshore or close to the, sorry, far away from onshore and close to the inshore? So is there any optimization method have been considered to show these areas?
We have not on this the maps that I showed you. I don't have here, I think I don't have all the results here on this presentation, but what we have done in another activity of the project was to define in some of the regions that were shown here on the map. We have tried and tested some configurations for example, 50 megawatt wind farms. And then we have optimized them having in mind the economic parameters. For example, we have optimized them in energy terms, in power production terms, but also by calculating the LCOE that you would have.
Sustainability as well.
Sustainability, yeah,
yes.
yeah. We have done that for floating, for fixed, and also for waves. So what has resulted, I can then on another day show you that we have developed a techno-economic tool. So you are able to prioritize your projects. For example, if you test one technology and then on another run you test another with different parameterizations, you can then select which one is the better for the region that you are studying. So that, yeah,
excellent.
That was.
Thank you. I have a question from Visa here, saying that in your presentation you showed some values for electrical losses and so on. What do you think about this? Are they high or within limits? Also, I want to emphasize the problem of connection to the transmission or distribution network. I think that some condition must be met and the TSO, DSO must be connected first so that the planning is more appropriate.
Yeah, that's absolutely true. In fact, this is when I started this, I said that this project is still going on, although officially ended. But in fact, we are using all these results and all of this in order to optimize and define the suitable areas for offshore in a working group where you have also the TSOs involved and environment entities and all of that. But that's absolutely true. About the limits, are they high or within limits? We try to be a little bit conservative in this case. So you can, for example, consider that one or two limits. I would say, for example, the electrical loss may be a little high, but not too high. Okay, so we can probably load them 1% or something like that, but they are mainly according to our experience for onshore, because we don't have that much for offshore, but on onshore, and also based on some literature that we have reviewed for this purpose, they are more or less acceptable.
Right.
Hello.
Thank you, Teresa. So Carlos, yes.
Good morning, everybody. Sorry, I could not join in the very first beginning of your presentation. Anyway, I think I got most of it and the conclusions. And I would like to thank the organizers of this webinar, and most of all to thank Teresa for giving this so very nice overview of this interesting project. And I have just a question. Maybe it's a bit philosophical at this point, but people and mostly politicians are talking a lot about having the connection of our electrical grid, and also some production of hydrogen and transferring this hydrogen to other parts of Europe, mostly to north of Spain and to France, and now recently also to Germany. For sure, you did not consider this in your in the development of this project, because this probably will also be an important parameter to take into account, because this will be probably in some specific parts in Portugal. Did you take that into account, or do you think this could be important in the future to have into account?
Yes, yeah. Thank you. That's a very, very interesting topic. In fact, in this project, we didn't think about hydrogen, but we are. That is a concern, and I think that we can improve this work by including it. We have already developed the first version of the Hydrogen Atlas for Portugal. We have a group here working on that, and that crossed my mind when I was going through the topics of this course. I thought to myself, this would be very interesting, very relevant, because you can use the accident of power production from the wind farms, whether onshore or offshore, to feed the electrolyzers.
Some voice glitching.
I think this is in fact very relevant in the short term, because sometimes I feel frozen.
Yes.
Yeah.
Were you able to listen to what I said? Because sometimes I see the image.
Well,
most of all.
Okay. I'm
Thank
sorry.
you. Yeah, thank you very much.
Right. So thank you very much for all of you, and thank you. Special thanks for Teresa for offering
Thank
to
you.
present today, for very, very nice and excellent topic and presentation. And please watch out for the announcement for the next webinar for the next month. Thank you very much, and I will send this recording to Triana to put in the website. Then you can watch it anytime and disseminate it as much as you can to your students, your colleagues, and anyone he might or she might be interested in. Thank you very much.
Thank you.
Thank you. Bye.
Bye-bye.
Yeah, thank you.
Thank
Bye.
you. Bye-bye. Good afternoon.
Bye.
Bye.
Thank you so much.